Hello, my name is Gemehl. I'm a student in Nuclear Technologies Energy, and I will present to you in this video the nuclear fuel cycle. The various activities associated with the production of electricity from nuclear reaction are referred to as the nuclear fuel cycle. It starts with the mining of the specific ore and ends with disposal of nuclear waste. With the reprocessing of spent fuel as an option for nuclear energy, we can close the nuclear fuel cycle, as I will explain further on. A majority of reactors currently in activity are light water reactors, which are designed to use uranium as a main fuel. Uranium is a chemical element with symbol U and atomic number 92 of the actinide family, which are the elements of atomic number between 89 and 103. It is a naturally radioactive element which doesn't possess any stable isotope. It is a relatively common natural element from the perspective of abundance, which is higher than that of silver, comparable to that of arsenic, but 4 times less than that of thorium. It is a constituent of most rocks and even of the sea, and can therefore be found everywhere with a concentration depending on location, from 200,000 ppm in Canada to 0.003 ppm in the seawater. Uranium ore can be mined by underground or open pit mining methods, and modern leaching methods as well, depending on the depths and the composition of the underground. The following tables gives some idea of our present knowledge of our uranium resources. It can be seen that Australia has a substantial part, about 29% of the world's uranium, Kazakhstan 12%, Russia 9%, and Canada 8% only. In nature, uranium is found as a mix of the following 3 isotopes: uranium-238, uranium-235, and a very small amount of uranium-234. However, only the uranium-235 is a fissile isotope, meaning that only 0.7% of the extracted uranium is available for nuclear fission. After mining, the ore is crushed and purified. Then it is treated with acid to dissolve the uranium, which is then recovered from solution. Right after being extracted, the uranium ore is treated to be uranium oxide, commonly called yellow cake, which is not significantly radioactive and which can be transported safely. Before it can be used in a reactor for electricity generation, however, it must undergo a series of processes to produce a usable fuel. For most of the world's reactors, the next step in making a usable fuel is to convert the uranium oxide into uranium hexafluoride. As a gas, it undergoes what we call the enrichment process to increase the uranium-235 content from 0.7% to about 4 to 5%. A byproduct, sometimes considered as the waste product of enrichment, is depleted uranium, which contains mainly uranium-238. It has the potential to be used in fast breeder reactors as a fertile material. By capturing a neutron, the uranium-238 nucleus is transformed into plutonium-239, which is fissile and can therefore be fissioned to produce energy. After enrichment, the uranium hexafluoride is converted to uranium dioxide, which is pressed into fuel pellets. These solid fuel pellets are placed inside long, thin metal tubes, which are assembled into bundles to become the fuel elements of the reactor core. In between the fuel rods, control rods made up of neutron-absorbing materials can be moved up and down to control the fission chain reaction in the reactor core. After a period of typically 4 years of irradiation time, the spent reactor fuel is removed from the core and stored, either to be reprocessed or disposed of in deep geological repositories. Even after exposure of 4 years in the reactor core, the used fuel still contains large quantities of uranium. By chemical processes, it is possible to separately recover both the uranium and the plutonium, which both contains potential fissile elements that can be reused later. Thorium, as well as uranium, can be used as a nuclear fuel. Thorium 2 and 32, is not fissile itself, but can be transmuted into uranium-233, which is an excellent fuel. In this regard, thorium is similar to uranium-238, which transmutes into plutonium-239. All thorium fuel concepts therefore require that thorium is first irradiated in a reactor core to produce the intermediate nuclide protactinium-233, which decays to uranium-233 with half-life of about 1 month. The thorium fuel cycle can best be applied in a new type of nuclear reactor with a liquid fuel, the so-called molten salt reactor. The use of thorium as a new primary energy source has been a promising prospect for many years. Extracting its latent energy value in a cost-effective way remains a challenge and requires considerable R&D efforts. The same applies for the R&D needed for the molten salt reactor. Today, there are 7 types of reactor into which thorium can be introduced as a nuclear fuel. The first 5 of these have all entered into operational service at some point in the past, while the last 2 are still conceptual. We'll be introducing them in the next video with a particular focus on the MSFR, molten salt fast reactor.